Welcome to Tech with Kaushik. This is set 19 of our DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link in the description. Let us begin set 19. Question number 338. Let's go. This one focuses on ECS auto-scaling. Scenario. A DevOps engineer supports a critical Java application deployed on an Amazon Elastic Container Service, Amazon ECS, cluster using AWS Fargate. The application must scale dynamically based on real-time demand. Extensive load testing indicates that the Java Virtual Machine, JVM, thread count is the most accurate indicator of application load. The container exposes these JVM metrics in Prometheus format on port 9404. The engineer must configure an auto-scaling solution for the ECS service based on this JVM thread count. Which approach fulfills this requirement with the least operational overhead? Choices. Option A. Add the AWS distro for OpenTelemetry, ADOT, collector as a sidecar container to scrape port 9404 and export the JVM metrics to Amazon Managed Service for Prometheus, AMP. Create a target tracking scaling policy in ECS using the AMP metric directly as the target. Option B. Add the Amazon CloudWatch agent as a sidecar container to scrape the Prometheus metrics from port 9404. Configure the agent to publish the metrics natively to Amazon CloudWatch using embedded metric format, EMF. Create a target tracking scaling policy in ECS utilizing the resulting CloudWatch custom metric. Option C. Add the Amazon CloudWatch agent as a sidecar container. Configure it to write raw logs to a CloudWatch logs group. Create a CloudWatch logs metric filter to extract the JVM thread count. Attach a step scaling policy to the ECS service to scale based on CloudWatch alarms triggered by the metric filter. Option D. Create an AWS Lambda function that runs every minute to pull port 9404 of the Fargate tasks. Configure the Lambda function to publish a custom metric to Amazon CloudWatch. Create a step scaling policy in ECS based on CloudWatch alarms. In this case, choose option B. Add the Amazon CloudWatch agent as a sidecar container to scrape the Prometheus metrics from port 9404. Configure the agent to publish the metrics natively to Amazon CloudWatch using embedded metric format, EMF. Create a target tracking scaling policy in ECS utilizing the resulting CloudWatch custom metric. Here's why. Application auto-scaling, used by ECS, natively relies on Amazon CloudWatch metrics for target tracking scaling policies. The Amazon CloudWatch agent has built-in support for scraping Prometheus endpoints. By deploying it as a sidecar in the ECS task, it can scrape port 9404 and export the metrics directly to CloudWatch's custom metrics using the embedded metric format, EMF. This allows you to immediately attach a target tracking policy to the ECS service using that metric with very low operational overhead. Now let's rule out the other options. A. While ADOT can send metrics to AMP, application auto-scaling does not natively integrate with AMP metrics for target tracking policies. You would have to build a complex intermediary system to push AMP alerts to CloudWatch or SNS. C. Writing raw text logs and parsing them with metric filters is unnecessary when the CloudWatch agent can natively scrape the Prometheus endpoint and emit structured metrics. Target tracking is also vastly superior to step scaling for dynamic, low-overhead capacity management. D. Using an external Lambda function to pull metrics from Fargate tasks is incredibly difficult because Fargate tasks are ephemeral and you would need to manage network discovery, IP routing, and rapid polling intervals. A sidecar container is the standard pattern for ECS telemetry. Exam tip. The Amazon CloudWatch agent can natively scrape Prometheus metrics and publish them as CloudWatch custom metrics. Target tracking policies provide the least operational overhead for auto-scaling. Next, question number 339. A global enterprise must deploy an Amazon API Gateway REST API to support a highly distributed client application. The business requires the API to be deployed redundantly across 3 different AWS regions to ensure independent availability in each geography. Clients must access the API using a single custom domain name. The architecture must direct clients to the AWS region, providing the fastest response time based on their geographic location. Which solution satisfies these constraints? Options. Option A. Deploy an edge-optimized API gateway endpoint in a single primary region. Create a custom domain in that region. Configure an Amazon Route 53 geo-proximity routing policy pointing to the edge-optimized API URL. Option B. Deploy regional API gateway endpoints in all 3 AWS regions. Create an API gateway custom domain in each of the 3 regions. Create an Amazon Route 53 alias record set utilizing a latency routing policy that points to the regional custom domains. Option C. Deploy an edge-optimized API gateway endpoint in the primary region. Integrate it with AWS Global Accelerator. Create an Amazon Route 53 alias record set pointing the custom domain to the Global Accelerator DNS name. Option D. Deploy regional API gateway endpoints in all 3 regions. Create a single Amazon CloudFront distribution mapping to all 3 API gateway invoke URLs as origins. Use an Amazon Route 53 simple routing policy pointing to the CloudFront distribution. Go with Option B. Deploy regional API gateway endpoints in all 3 AWS regions. Create an API gateway custom domain in each of the 3 regions. Create an Amazon Route 53 alias record set utilizing a latency routing policy that points to the regional custom domains. This works because to provide independent availability in multiple regions, the API architecture must be deployed redundantly, meaning the infrastructure must physically exist in each target region. A regional API gateway endpoint keeps API execution within that specific region. By configuring a custom domain in each region and utilizing Route 53 latency-based routing, clients using the single custom domain are seamlessly directed to the region that offers the lowest network latency. The other choices do not work because an edge-optimized API gateway is deployed in a single region, usually East 1, and relies on cloud front-edge locations for ingestion. It does not provide independent, redundant regional availability for the backend processing. If the primary region fails, the API goes down. C. Similar to A, an edge-optimized endpoint exists in only one region. Putting Global Accelerator in front of a single region deployment does not satisfy the requirement for multi-region independent availability. D. You cannot simply place a custom CloudFront distribution in front of multiple API gateway instances and rely on a simple routing policy to achieve latency-based routing. Route 53 latency routing integrated directly with regional API gateways is the correct architectural pattern. The main takeaway is for true multi-region active redundancy in API gateway. Always deploy regional endpoints and use Route 53 latency routing to direct clients to the optimal region. Now for question number 340. Here's the scenario. An auto-scaling group processes payloads asynchronously from an Amazon Simple Queue service, Amazon SQS queue. Recently, a downstream API failure caused payloads to take exceptionally long to process, causing the queue depth to swell far beyond baseline expectations and disrupting dependent systems. A DevOps engineer must implement an automated alert to an existing Amazon Simple Notification Service, Amazon SNS, topic if the queue depth becomes dangerously high again. Which solution will meet this requirement most efficiently? Review the options. Choice A. Create an Amazon CloudWatch metric alarm targeting the approximate number of messages visible SQS metric. Set a static threshold above the baseline expectation and configure the alarm action to notify the SNS topic. Choice B. Create an Amazon CloudWatch metric alarm targeting the approximate number of messages delayed SQS metric. Set a static threshold above the baseline expectation and configure the alarm action to notify the SNS topic. Choice C. Create an AWS Lambda function that retrieves the approximate number of messages SQS queue attribute and publishes it as a custom CloudWatch metric. Trigger the Lambda via EventBridge every minute. Create an alarm on this custom metric that notifies the SNS topic. Choice D. Enable SQS dead letter queues. Configure an EventBridge rule that monitors the dead letter queue for new messages and triggers a Lambda function to send a notification to the SNS topic. The best choice is option A. Create an Amazon CloudWatch metric alarm targeting the approximate number of messages visible SQS metric. Set a static threshold above the baseline expectation and configure the alarm action to notify the SNS topic. Amazon SQS natively publishes the approximate number of messages visible metric to Amazon CloudWatch at regular intervals. This metric represents the number of messages currently residing in the queue available for processing, the queue depth. Creating a CloudWatch metric alarm against this specific metric is the most direct and operationally efficient way to monitor if the queue size exceeds expected bounds, requiring no custom code or external compute. B. Approximate number of messages delayed measures messages that are in the queue but currently hidden from consumers because a delay queue setting or message timer was applied. It does not reflect a backlog of messages waiting to be processed. C. Creating a Lambda function to query SQS and publish a custom metric is redundant and adds operational overhead. SQS already publishes queue depth metrics to CloudWatch natively. D. While dead letter queues, DL queues, catch messages that fail processing multiple times, the scenario states payloads are taking exceptionally long to process, causing a queue buildup, not necessarily that they are failing and erroring out into a DL queue. Here's a useful exam tip. To monitor the active backlog depth of an SQS queue, always alert on the CloudWatch metric approximate number of messages visible. Question number 341. This question takes us into CloudTrail and S3 auditing. An enterprise utilizes AWS organizations to manage dozens of AWS accounts. A dedicated Amazon S3 bucket stores highly confidential financial data. The security team needs to query historical S3 object-level API activity for this specific bucket. Simultaneously, the security team requires automated anomaly detection for S3 access patterns across all AWS accounts in the organization. Which combination of services will meet these requirements with the least operational overhead? Option A. Create an AWS CloudTrail organization trail delivered to an S3 bucket in a central audit account. Enable S3 data events logging for all buckets. Use Amazon GuardDuty for anomaly detection across all accounts. Use Amazon Athena to perform SQL queries on the CloudTrail logs in the audit bucket. Option B. Create an AWS CloudTrail organization trail delivered to an S3 bucket in the management account. Enable S3 data events logging. Use Amazon Macie for anomaly detection across all accounts. Use Amazon CloudWatch metrics insights to perform SQL queries on the S3 bucket access logs. Option C. Create an AWS CloudTrail organization trail delivered to Amazon CloudWatch logs in the management account. Enable S3 data events logging. Use CloudWatch anomaly detection across all accounts. Use Amazon CloudWatch metrics insights to perform SQL queries on the CloudTrail logs. Option D. Create individual AWS CloudTrail trails in each AWS account delivered to Amazon CloudWatch logs. Enable S3 data events logging. Use Amazon GuardDuty for anomaly detection. Use Amazon Athena to perform SQL queries directly on the CloudWatch logs log groups. The answer here is option A. Create an AWS CloudTrail organization trail delivered to an S3 bucket in a central audit account. Enable S3 data events logging for all buckets. Use Amazon GuardDuty for anomaly detection across all accounts. Use Amazon Athena to perform SQL queries on the CloudTrail logs in the audit bucket. The main reason is an AWS CloudTrail organization trail automatically logs activity for all member accounts. Delivering these logs to an S3 bucket enables powerful SQL querying capabilities using Amazon Athena directly against the raw log files. To meet the security anomaly detection requirement natively, Amazon GuardDuty offers built-in S3 protection that uses machine learning to detect suspicious API activity, such as unusual data exfiltration or credential compromise, across the entire organization. Here's why the alternatives are not suitable. B. Amazon Macie is specifically designed to discover and protect sensitive data, like PI, inside S3 buckets by scanning the object contents. It is not designed to monitor CloudTrail logs for access anomalies. GuardDuty handles threat detection and access anomalies. C. CloudWatch Metrics Insights is used for querying time series metric data using SQL, not for querying complex JSON log payloads from CloudTrail. Athena is the correct tool for querying CloudTrail logs. D. Creating individual trails per account violates the requirement for minimal operational overhead in a multi-account environment. Organization trails enforce centralized, tamper-proof logging automatically. Furthermore, querying raw CloudWatch logs log groups via Athena is not native. Athena queries data stored in S3. A helpful shortcut is this. When asked to perform SQL analysis on historical CloudTrail logs, Amazon Athena plus Amazon S3 is the standard solution. For threat and anomaly detection on S3 API calls, Amazon GuardDuty S3 protection is the answer. Next up is question number 342. A company deploys an internal application through an Amazon API Gateway Private REST API. Company workloads invoke the API through interface VPC endpoints from a defined set of authorized VPCs. The API accesses a sensitive backend database. For compliance reasons, the private API must reject requests originating from any VPC that is not on the approved list. Which configuration will enforce this requirement? Here are the options. Option A. Create an AWS WAF Web ACL containing an IP set match rule for the authorized VPC CIDR ranges. Associate the Web ACL with the private API. Option B. Modify an inbound security group attached directly to the API Gateway Private REST API to allow HTTPS only from the authorized VPC CIDR ranges. Option C. Attach an API Gateway Resource Policy to the private REST API. Use the AWS Source VPC condition key to deny execute API. Invoke requests from VPC IDs that are not explicitly authorized. Option D. Attach an IAM role to the API Gateway Private REST API. Configure the role trust policy to allow role assumption only from the authorized VPC IDs. The right response is option C. Attach an API Gateway Resource Policy to the private REST API. Use the AWS Source VPC condition key to deny execute API. Invoke requests from VPC IDs that are not explicitly authorized. Let's look at the reasoning. For API Gateway Private REST APIs, resource policies can use AWS Source VPC or AWS Source VEPs to restrict invocation to specific VPCs or VPC endpoints. An explicit deny for requests whose source VPC is not approved enforces the network origin guardrail at the API. The remaining options can be eliminated because AWS WAF filters web requests but does not identify a caller by VPC ID. B. API Gateway Private REST APIs do not expose a customer-managed security group on the API itself. Security groups apply to the interface VPC endpoints. D. A role trust policy governs role assumption, not network-based invocation of the API endpoint. AWS Source VPC and AWS Source VEPs are valid API Gateway Resource Policy condition keys for private APIs. Make the private API prerequisite explicit. Question number 343. We're moving on to EC or vulnerability scanning. Consider this situation. A company operates a continuous integration pipeline where AWS code build generates container images and publishes them to Amazon Elastic Container Registry, Amazon ECR. The security team has noticed that vulnerabilities in container-based images are frequently missed until the images are deployed to production. The company must automatically scan images for vulnerabilities upon push and notify the security team immediately if severe issues are identified. Which combination of steps will meet these requirements with the least operational overhead? Choose two. More than one answer may be correct. Option A. Enable Amazon Inspector Enhanced Scanning for Amazon ECR and configure it to use continuous scanning. Option B. Create an Amazon Event Bridge rule that filters for Amazon Inspector findings. Configure the rule to target an Amazon Simple Notification Service, Amazon SNS, topic monitored by the security team. Option C. Enable basic scanning for Amazon ECR. Configure a Lambda function to continuously poll the ECR repository for new tags and execute an open-source vulnerability scanner. Option D. Create an AWS CloudTrail alarm that monitors for put image events and triggers an Amazon Simple Email Service, Amazon SES, notification. Option E. Enable AWS Code Guru security in the code build project to perform static analysis on the Docker file before the image is pushed to Amazon ECR. The correct answers are Option A. Enable Amazon Inspector Enhanced Scanning for Amazon ECR and configure it to use continuous scanning, and Option B. Create an Amazon Event Bridge rule that filters for Amazon inspector findings. Configure the rule to target an Amazon Simple Notification Service, Amazon SNS, topic monitored by the security team. This is the best choice because Amazon EC natively integrates with Amazon Inspector to provide enhanced vulnerability scanning. By configuring it for continuous scanning, Inspector automatically scans images upon push and continuously monitors them against the latest vulnerability databases. When Inspector detects a vulnerability, it emits a finding to Amazon Event Bridge. A simple Event Bridge rule can filter these findings and route them to an SNS topic to alert the security team immediately, fulfilling all requirements with minimal configuration. Let's quickly check the incorrect choices. C. Enabling basic scanning only scans images once upon push using the open-source Claire engine. Writing a custom Lambda function to pull ECR and execute a third-party scanner introduces massive operational overhead and custom code maintenance. D. AWS CloudTrail put image events do not contain vulnerability information. They only indicate that an image was pushed. Triggering SES from a CloudTrail alarm would just notify the team that a push occurred, not that a vulnerability was found. E. AWS CodeGuru Security is designed to perform static application security testing, SAST, on source code, like Python, Java. It does not scan compiled Docker container image layers or OS-level packages for CVE vulnerabilities. Keep this point in mind for the exam. Amazon ECR enhanced scanning uses Amazon Inspector under the hood. For event-driven security alerting on container images, route Amazon Inspector findings through Event Bridge to SNS. Here comes question number 344. Here's what is happening. An application uses an Amazon Aurora Postgres QL global database with a primary cluster in one AWS region and one secondary cluster in another region. To meet disaster recovery requirements, the DevOps engineer configured a managed recovery point objective, RPO, of 60 seconds. During recurring network degradation, Aurora global debar lag for the secondary cluster exceeds 60 seconds and write transactions on the primary cluster pause until the secondary catches up. The organization must retain the 60-second managed RPO setting but wants to reduce the likelihood that this single lagging secondary blocks commits. Which change best meets these requirements? The choices are: Choice A. Enable write forwarding on the secondary cluster so write traffic can be distributed across both regions. Choice B. Add another secondary cluster in a different region and verify that it can consistently maintain Aurora global debar lag below 60 seconds. Choice C. Remove the only secondary cluster from the Aurora global database and continue using the 60-second managed RPO setting. Choice D. Increase the RDS global _RPO setting from 60 seconds to 300 seconds. The right response is option B. Add another secondary cluster in a different region and verify that it can consistently maintain Aurora global debar lag below 60 seconds. Here's why. With managed RPO for Aurora Postgres QL global database, a primary transaction can commit when at least one secondary cluster has RPO lag below the configured threshold. Commits are blocked only when all secondary clusters exceed the RPO. Adding a healthy secondary that stays below 60 seconds removes the single secondary dependency while preserving the 60-second setting. Now let's rule out the other options. A. Write forwarding sends eligible writes from a secondary region to the primary. It does not reduce cross-region RPO lag. C. Removing the only secondary defeats the cross-region recovery design the managed RPO is intended to protect. D. Raising the RPO changes the required 60-second configuration. Exam tip. For Aurora Postgres QL managed RPO, commits continue when at least one secondary is within the RPO. Blocking occurs when all secondaries exceed it. Next, question number 345. Scenario. An enterprise uses AWS organizations to manage its multi-account environment. A newly acquired startup was just invited to the organization and placed into a dedicated organizational unit, OU. To control costs and comply with data sovereignty laws, the enterprise must enforce two strict rules on the startup's accounts. Developers may only launch T3.small Amazon EC2 instances, and these instances may only be launched within US-based AWS regions. For example, US, East 1, US, West 2. Which service control policy, SCP, configuration will enforce these restrictions effectively? Option A. Create an SCP with a deny statement for the EC2, Run instances action using a string not equals condition for EC2. Instance type set to t3.small. Create a second deny statement for EC2. Run instances using a string not like condition for AWS. Requested region set to us-star. Option B. Create an SCP with an allow statement for the EC2. Run instances action using a string equals condition for EC2. Instance type set to t3.small. Create a second allow statement using a string-like condition for AWS. Requested region set to us-star. Option C. Create an SCP with a deny statement for the EC2. Run instances action using a string equals condition for EC2. Instance type set to t3.small. Create a second deny statement using a string-like condition for AWS. Requested region set to us-star. Option D. Create an SCP with an allow statement for the EC2. Run instances action. Apply a string not equals condition for EC2. Instance type set to t3.small and a string not like condition for AWS. Requested region set to us-star. In this case, choose option A. Create an SCP with a deny statement for the EC2. Run instances action using a string not equals condition for EC2. Instance type set to t3.small. Create a second deny statement for EC2. Run instances using a string not like condition for AWS. Requested region set to us-star. This works because service control policies, SCPs, do not grant permissions. They act as guardrails. The most effective way to restrict access to specific resource types and regions in an SCP is to use an explicit deny combined with negative condition operators, string not equals, string not like. If a developer requests anything other than t3.small, the first statement blocks it. If they request a region that does not start with us-, the second statement blocks it. An explicit deny in an SCP overrides any allow permissions granted by the IAM policies within the account. The other choices do not work because B. Using allow statements in an SCP merely sets the maximum possible permissions. If the SCP allows t3.small but doesn't explicitly deny other types, a user with administrator access can still launch am5.large unless the SCP blocks it, or unless the SCP implicitly denies by omitting EC2, run instances entirely. However, explicit deny with negative conditions is the standard AWS best practice for these guardrails. C. Using a deny statement with a string equals condition for t3.small would explicitly prevent the startup from launching the only instance type they are supposed to use. D. As with B, an allow statement with negative conditions is ineffective as a firm guardrail. It just means the SCP doesn't allow those other types, but it doesn't strictly deny them if they fall under another broad allow. Explicit deny is required. The main takeaway is to enforce strict guardrails via SCPs, like allowed regions or allowed instance types. Always use a deny effect combined with negative conditions, for example, string not equals, string not like. Here comes question number 346. Next, let's move into guardrails and SCPs. Here's the scenario. A centralized security team utilizes AWS CloudTrail organization trails to log all API activity across an AWS organization's environment. The security team has identified instances where privileged users and member accounts have intentionally disabled local logging capabilities. The security team must implement an irreversible preventative control to ensure no identity in any member account can halt CloudTrail logging or delete trails. Which implementation meets this requirement? Choice A. Attach a service control policy, SCP, to the organization root containing a deny effect for the CloudTrail, stop logging and CloudTrail, delete trail actions. Choice B. Deploy an AWS IAM permissions boundary to all member accounts via AWS Cloud Formation stack sets that restricts access to the CloudTrail, stop logging action. Choice C. Configure an Amazon Event Bridge rule in all member accounts to trigger an AWS config auto-remediation runbook that immediately restarts CloudTrail if logging is stopped. Choice D. Create IAM resource-based policies on the CloudTrail S3 buckets that deny the S3, delete object, and CloudTrail. Stop logging actions for member account principals. Go with option A. Attach a service control policy, SCP, to the organization root containing a deny effect for the CloudTrail, stop logging and CloudTrail, delete trail actions. Service control policies, SCPs, provides centralized control over the maximum available permissions for all accounts in an AWS organization. By placing an explicit deny on CloudTrail, stop logging, and CloudTrail, delete trail at the root, or specific OU, the action is blocked globally. Because SCPs override local IAM policies, even the root user of a member account or a principal with administrator access will be prevented from executing these actions, ensuring an irreversible preventative guardrail. B. IAM permissions boundaries must be attached to individual IAM users and roles. Privileged users in the member account could simply detach the boundary or create new roles without the boundary, bypassing the control. C. AWS config auto-remediation is a detective and reactive control, not a preventative one. The trail would be stopped momentarily, creating a logging gap, and a privileged user could simply disable the config rule. D. Resource-based policies on S3 buckets protect the log files from deletion, but they cannot prevent users from invoking the CloudTrail stop logging API to halt the generation of new logs. Here's a useful exam tip. Whenever a scenario requires an irreversible, organization-wide preventative control to block specific actions, even for administrators, a service control policy, SCP, with an explicit deny is the correct solution. Now for question number 347. Here's what is happening. A company runs hundreds of Amazon EC2 instances in a single AWS account. New instances are frequently launched and terminated by automated scaling processes, while some core infrastructure instances have been running for months. A security audit mandates that every running EC2 instance must have an IAM instance profile attached for centralized monitoring agents. A default IAM role with the required monitoring permissions has been created. The DevOps team must automatically attach this role to any existing or newly launched instance that lacks an instance profile. Which solution fulfills this requirement with the least operational overhead? Here are the options. Option A. Enable AWS config. Deploy the EC2 instance profile, attached managed rule, and configure automatic remediation with the AWS attach M2 instance systems manager automation runbook, passing the default IAM role name as role name. Option B. Configure an Amazon Event Bridge rule for run instances API calls. Route events to a Lambda function that attempts to halt the launch, attach the default role, and resume the launch. Option C. Attach an IAM permissions boundary to all IAM users that denies EC2. Run instances unless the request includes the default IAM instance profile ARN. Option D. Create an AWS config custom Lambda rule that evaluates every hour and terminates any instance that does not have an instance profile. The best choice is option A. Enable AWS config. Deploy the EC2 instance profile, attached managed rule, and configure automatic remediation with the AWS attach M2 instance systems manager automation runbook, passing the default IAM role name as role name. The main reason is the AWS config managed rule flags an EC2 instance as non-compliant when no IAM instance profile is attached. AWS attach M2 instance accepts instance ID and the required role name parameter, locates or creates an instance profile for that role, and attaches it. Config automatic remediation therefore covers both existing and newly changed instances without custom code. Here's why the alternatives are not suitable. B. Event Bridge is not an inline control that can pause and resume run instances, and this pattern would not remediate already running instances. C. A permissions boundary limits permissions. It does not inject an instance profile into requests or remediate existing instances. D. A custom periodic rule and termination workflow adds code and disruption when a managed config rule and AWS runbook already exist. A helpful shortcut is this. For AWS config remediation, verify the exact systems manager runbook parameters. AWS attach M2 instance takes role name, not an instance profile name. Question number 348. Take extra care here because this is a hard question. A web application is deployed to an Amazon Elastic Kubernetes Service, Amazon EKS, cluster. The cluster's data plane relies entirely on AWS Fargate profiles, eliminating EC2 worker nodes. Recently, the application has experienced intermittent latency spikes. A DevOps engineer has been asked to export detailed metrics and traces to Amazon CloudWatch and AWS X-Ray to troubleshoot the issue. The security team mandates that the observability agents must operate with least privilege IAM permissions attached directly to the application pods. Which combination of steps is required to implement this solution? Choose 3. Identify all valid responses. Options. Option A. Configure an IAM OpenID Connect, OIDC, provider for the EKS cluster. Option B. Use IAM roles for service accounts, IRSA, to associate a Kubernetes service account with an IAM role containing the CloudWatch agent server policy and AWS XRAI only access managed policies. Option C. Deploy the AWS distro for OpenTelemetry, ADOT, collector as a sidecar container or Kubernetes deployment to process and export the telemetry data. Option D. Deploy the AWS distro for OpenTelemetry, ADOT, collector as a Kubernetes daemon set to capture logs and metrics from the Fargate infrastructure. E. Use IAM roles for service accounts, IRSA, to associate a Kubernetes service account with an IAM role containing the administrator access policy to ensure Fargate pod execution works correctly. F. Modify the Fargate execution role to include the Amazon EKS policy and attach it to the kubesystem namespace. The required selections are Option A. Configure an IAM OpenID Connect, OIDC, provider for the EKS cluster. Option B. Use IAM roles for service accounts, IRSA, to associate a Kubernetes service account with an IAM role containing the CloudWatch agent server policy and AWS XRAI only access managed policies. And Option C. Deploy the AWS distro for OpenTelemetry, ADOT, collector as a sidecar container or Kubernetes deployment to process and export the telemetry data. Let's look at the reasoning. To export metrics and traces to AWS services securely from EKS on Fargate, the pods require IAM permissions. EKS utilizes an IAM OIDC provider to federate Kubernetes identities with AWS IAM. IAM roles for service accounts, IRSA, maps a Kubernetes service account to an IAM role. This adheres to the principle of least privilege by attaching permissions, CloudWatch and XRAI, directly to the application pod rather than underlying infrastructure. Because AWS Fargate does not allow access to the underlying host, you cannot deploy cluster-wide agents as daemon sets. Observability agents like the ADOT collector must be deployed as a sidecar container injected into the application pod, or as a standard Kubernetes deployment. The remaining options can be eliminated because Kubernetes daemon sets are not supported on EKS Fargate. Fargate provisions a dedicated micro VM for each pod, meaning there are no shared worker nodes on which a daemon set can run. Attaching administrator access to application pods drastically violates the security mandate for least privilege permissions. F. The Fargate execution role is used by the kubelet to pull images and start the pod. It is not used by the application code or sidecar containers running inside the pod to communicate with AWS services like CloudWatch. EKS on Fargate does not support daemon sets. To implement observability, you must use sidecar containers like ADOT or FluentBit and provide IAM permissions via IRSA, IAM roles for service accounts. Next up is question number 349. Consider this situation. A development team maintains application source code in an AWS code commit repository and deploys via an AWS code pipeline. To improve application security, the company mandates that all source code must be statically analyzed for vulnerabilities during the CI/CD process. If a vulnerability is detected, the deployment process must halt immediately before reaching the production environment. Which integration meets these requirements? Review the options. Choice A. Create an AWS code build project that executes an Amazon Code Guru security scan on the source code. Configure the code build project to fail if vulnerabilities are found. Add this code build project as a new action stage in code pipeline prior to the deployment stage. Choice B. Add a new stage in code pipeline before the deployment stage. Select Amazon Inspector as the action provider and configure it to scan the code commit source artifact directly for vulnerabilities. Choice C. Attach an IAM role to code pipeline containing permissions for Amazon Macie. Configure Macie to monitor the artifact S3 bucket and trigger a Lambda function to stop the pipeline if sensitive data vulnerabilities are discovered. Choice D. Create an AWS code build project that executes Amazon DevOps Guru. Configure DevOps Guru to perform static application security testing, SEST. Add this code build project as a stage before deployment. The answer here is option A. Create an AWS code build project that executes an Amazon Code Guru security scan on the source code. Configure the code build project to fail if vulnerabilities are found. Add this code build project as a new action stage in code pipeline prior to the deployment stage. This is the best choice because Amazon Code Guru Security is a machine learning-driven service optimized for scanning application source code for security vulnerabilities, static application security testing. By wrapping the Code Guru security scan in an AWS code build project, you can natively integrate it as a stage in AWS code pipeline. If Code Guru detects a vulnerability, the code build step exits with a failure code, which naturally halts the code pipeline execution before it reaches the deployment stage. Let's quickly check the incorrect choices. B. Amazon Inspector is designed to scan Amazon EC2 instances, Lambda functions, and compiled container images in Amazon EC are for CVs. It does not scan raw source code directly from code commit. C. Amazon May-C is a data security service used to discover and protect sensitive data, like PI or credit card numbers, stored in Amazon S3. It is not an application source code vulnerability scanner. D. Amazon DevOps Guru is an ML-powered service that identifies operational anomalies in production environments, like latency spikes or memory leaks. It does not perform static application security testing, SCSD, on source code. Keep this point in mind for the exam. For static source code security scanning, SCSD, embedded in a CI/CD pipeline, Amazon Code Guru Security integrated via AWS Code Build is the appropriate tool. Question number 350. Let's go. The focus now shifts to code pipeline automated testing. Scenario. An AWS code pipeline automates the build and deployment of a web application to an Amazon Elastic Container Service, Amazon ECS, cluster. Occasionally, a faulty deployment causes the web application's main URL to return a 503 HTTP status code, even though the code deploy action succeeds. A DevOps engineer must implement an automated verification test immediately following the deployment stage. The test must request the homepage URL and ensure it returns a 200 OK HTTP status code. If the test does not receive a 200 OK, the pipeline must explicitly fail. Which solution will implement this automated verification natively within the pipeline? Choices. Option A. Create an AWS Lambda function that makes an HTTP GET request to the application URL, checks the response code, and calls the put_job_success_result or put_job_failure_result code pipeline APIs. Add an invoke action stage in code pipeline targeting this Lambda function. Option B. Create an Amazon CloudWatch synthetics canary that monitors the application URL. Add a CloudWatch action stage in code pipeline configured to wait for the canary's next scheduled run to succeed. Option C. Add an AWS code deploy verification action to the pipeline. Supply the application URL as an input artifact and configure the action to halt the pipeline if the endpoint returns anything other than 200 OK. Option D. Add an Amazon API Gateway HTTP API stage in code pipeline. Configure the API gateway to route a request to the application URL and map a 503 response directly to a code pipeline failure event. The best choice is option A. Create an AWS Lambda function that makes an HTTP GET request to the application URL, checks the response code, and calls the put_job_success_result or put_job_failure_result code pipeline APIs. Add an invoke action stage in code pipeline targeting this Lambda function. Here's why. AWS code pipeline natively supports triggering AWS Lambda functions as a custom action stage, the invoke action. The Lambda function receives a unique job ID from code pipeline in the event payload. The function executes its custom logic, making the HTTP request, verifies the response code, and then explicitly returns a success or failure signal back to code pipeline using the put_job_success_result or put_job_failure_result API calls. This is the standard, least overhead method for custom verification tests in code pipeline. Now let's rule out the other options. B. Code pipeline does not have a native CloudWatch action that can wait for a synthetics canary to run. While you can trigger pipelines from CloudWatch events, injecting a synchronous pause in a pipeline to wait for a scheduled canary requires complex custom step function logic. C. AWS Code Deploy is used strictly to deploy application artifacts to compute platforms, EC2, ECS, Lambda. It does not have a built-in verification action that performs HTTP requests against an arbitrary URL. D. Code pipeline cannot use API gateway as an action stage. You can trigger a pipeline via an API gateway webhook, but you cannot embed an API gateway as a testing step within the pipeline's execution flow. Exam tip: when you need to perform custom testing or verification logic as a stage inside AWS code pipeline, use the AWS Lambda invoke action and ensure the Lambda calls put job success result or put job failure result. Question number 351. A web application writes access logs as JSON objects to an Amazon CloudWatch logs log group. Each log event contains fields such as response_code and application_name. The operations team needs a real-time CloudWatch metric that tracks the rate of requests. This metric must allow operators to filter and group the data visually on a CloudWatch dashboard by the specific response_code, for example, 200 for 104, 500, and application_name. Which approach fulfills this requirement most efficiently? The choices are: Option A, create a CloudWatch logs metric filter on the log group. Define a filter pattern that matches the JSON structure. Configure the filter to publish a metric value of 1 and define response_code and application_name as metric dimensions. Option B, run an Amazon CloudWatch logs insights query against the log group using the stats count function grouped by response_code and application_name. Save the query directly as a CloudWatch custom metric. Option C, configure an Amazon event bridge rule that triggers on new log streams. Route the events to an AWS Lambda function that parses the JSON logs and explicitly calls the put metric data API using response_code and application_name as dimensions. Option D, create an Amazon Kinesis data firehose delivery stream attached to the log group. Transform the records using AWS Lambda and output the results directly to CloudWatch metrics as multidimensional data points. The right response is option A. Create a CloudWatch logs metric filter on the log group. Define a filter pattern that matches the JSON structure. Configure the filter to publish a metric value of 1 and define response_code and application_name as metric dimensions. This works because CloudWatch logs metric filters allow you to extract numerical data from log events and publish it directly to CloudWatch metrics in real time. Crucially, metric filters natively support extracting fields from JSON log events to use as metric dimensions. By defining response_code and application_name as dimensions, CloudWatch will automatically generate unique time series metrics for every combination of those fields, allowing operators to easily group and graph the data on a dashboard with no custom compute overhead. The other choices do not work because B, CloudWatch Logs Insights, is an ad hoc query engine. While it can aggregate data visually in the console, it does not continuously publish real-time CloudWatch metrics that can be directly added to a standard dashboard widget or used for alarms. C, triggering a Lambda function for every log stream to parse JSON and call put metric data involves significant custom code, latency, and Lambda invocation costs. Metric filters handle this natively at the log group layer. D, routing logs through Kinesis data firehose to Lambda just to extract metrics is an overly complex architectural anti-pattern when CloudWatch Logs provides this extraction natively via metric filters. The main takeaway is if you need real-time, multidimensional CloudWatch metrics generated directly from structured JSON application logs, use CloudWatch Logs metric filters with defined dimensions. Next, question number 352. A legacy workload was recently migrated to AWS using a simple lift and shift approach. The entire stack, a Python web application, a PostgreSQL database, and a REDISS caching layer, runs on a single monolithic Amazon EC2 instance. As user traffic has grown, the instance frequently runs out of memory, causing significant latency and periodic downtime. The DevOps team must redesign the architecture to separate the application components, eliminate single points of failure, and provide automatic scaling for the web tier. Which target architecture meets these requirements? Options. Option A. Deploy the web application to an auto-scaling group behind an application load balancer, ALB. Migrate the PostgreSQL database to an Amazon Aurora PostgreSQL multi-availability zone cluster. Migrate the REDISS cache to an Amazon Elastic Cache for REDISS multi-availability zone cluster. Option B. Deploy the web application to an auto-scaling group behind a network load balancer, an LB. Keep the PostgreSQL database on a dedicated EC2 instance attached to an auto-scaling group of size 1. Migrate the RedISS cache to Amazon MemoryDB. Option C. Deploy the web application to an auto-scaling group behind an application load balancer, ALB. Migrate the PostgreSQL database to an Amazon RDS single availability zone instance with automated backups enabled. Leave the RedISS cache running locally on the web EC2 instances to reduce network latency. Option D. Migrate all three components into separate Docker containers. Run the containers on a single massive EC2 bare metal instance using AWS Elastic Beanstalk to ensure they are automatically restarted if they crash. In this case, choose option A. Deploy the web application to an auto-scaling group behind an application load balancer, ALB. Migrate the PostgreSQL database to an Amazon Aurora PostgreSQL multi-availability zone cluster. Migrate the RedISS cache to an Amazon Elastic Cache for RedISS multi-availability zone cluster. To resolve the memory bottlenecks and single points of failure of the monolithic architecture, the components must be decoupled. The web application is stateless and HTTP-based, making an application load balancer, layer 7, paired with an auto-scaling group, the perfect solution for horizontal scaling. Migrating the database to Amazon Aurora PostgreSQL multi-availability zone provides a highly available, managed database tier that scales compute and storage independently. Moving the cache to Amazon Elastic Cache for RedISS in a multi-availability zone configuration ensures the cache survives node failures and offloads memory pressure from the web tier. B. A network load balancer, layer 4, is less suitable for a standard web application than an ALB, which provides advanced HTTP routing. More importantly, keeping the database on a single EC2 instance retains the primary single point of failure and management overhead. C. Leaving the RedISS cache running locally on the web EC2 instances defeats the purpose of decoupling. If the auto-scaling group scales in, the local cache data is lost. Furthermore, a single availability zone RDS instance is not highly available. D. Running containers on a single massive bare metal instance does not eliminate the single point of failure. If the underlying physical host experiences a hardware fault, the entire application stack still goes down. Here's a useful exam tip. When breaking apart a monolithic web stack for high availability, place the web tier in an ASG behind an ALB. Move the database to managed RDS/Aurora multi-availability zone, and move caching to Elastic Cache. Question number 353. We're moving on to multi-account governance. Scenario. A cloud engineering team is establishing a governance strategy for a new multi-account AWS organization's environment. The business has strict regulatory requirements. AWS resources must only be provisioned in the EU Central 1 and EU West 1 regions. Developers must only be permitted to use a pre-approved list of AWS services, for example, EC2, S3, or DS. Corporate Active Directory must be used for authentication. Access permissions for specific job functions, for example, database admin, network admin, must be consistent across all member accounts. Which combination of AWS features will implement this governance model? Choices. Option A. Apply a service control policy, SCP, at the organizational root to restrict the allowed regions and services. Use AWS Cloud Formation Stack sets to deploy IAM roles for each job function into every member account, configuring the trust policies to integrate with the Active Directory SAML identity provider. Option B. Apply IAM permissions boundaries to all IAM users via AWS Systems Manager automation to restrict the allowed regions and services. Use AWS Directory Service for Microsoft Active Directory to replicate on-premises users directly into AWS IAM as IAM users. Option C. Apply a service control policy, SCP, at the organizational root to restrict the allowed regions and services. Use AWS Resource Access Manager, AWS RAM, to share centralized IAM Identity Center roles from the management account to the member accounts. Option D. Use AWS Cloud Formation Stack sets to deploy a global AWS WAF Web ACL to restrict regional API access. Configure AWS IAM Identity Center, AWS Single Sign-On, in the management account and map Active Directory groups to locally created IAM users in each member account. Go with option A. Apply a service control policy, SCP, at the organizational root to restrict the allowed regions and services. Use AWS Cloud Formation Stack sets to deploy IAM roles for each job function into every member account, configuring the trust policies to integrate with the Active Directory SAML identity provider. The main reason is the requirements dictate restrictive guardrails, regions, and services alongside consistent, federated authentication, Active Directory, mapped to job functions. Service control policies, SCPs, are the native tool in AWS organizations to enforce maximum available permissions, restricting which regions and AWS services can be accessed globally across the organization. AWS Cloud Formation Stack sets allow the centralized deployment of IAM roles to all member accounts simultaneously. By configuring these IAM roles with SAML trust policies pointing to the corporate Active Directory, users can federate directly into the specific roles corresponding to their job functions. Here's why the alternatives are not suitable. B. IAM permissions boundaries restrict individual identities, but managing them at scale via SSM is operationally complex and error-prone compared to SCPs. Syncing AD users to IAM users as a long-term strategy is an AWS anti-pattern. SAML/OIDC federation should be used instead of creating static IAM users. C. AWS Resource Access Manager, AWS RAM, is used to share infrastructure resources, like VPC subnets or transit gateways, between accounts. It cannot be used to share IAM roles from the management account to member accounts. D. AWS WAF is a web application firewall used to protect web applications. It cannot restrict AWS API actions regionally. Also, creating local IAM users for AD groups defeats the purpose of federation. A helpful shortcut is this. Use AWS organizations' SCPs to enforce broad guardrails, like allowed regions. Use Cloud Formation Stack sets to deploy consistent baseline resources, like federated IAM roles, across multiple accounts. Question number 354. Let's go. A DevOps team relies heavily on public Node Package Manager, NPM, libraries to build a front-end application. AWS Code Build currently downloads these libraries directly from npmjs.com. The company wants to use a private, managed AWS repository for dependencies. The security team requires each newly introduced public package version to pass an automated vulnerability check before developers or normal CI builds can download that version from the approved repository. Which solution meets these requirements with the least operational overhead? Option A. Create two AWS code artifact repositories in the same domain. A restricted quarantine repository with an external connection to npmjs.com and an approved repository without a public upstream. Use an automated code pipeline/code build ingestion workflow to fetch candidate versions into quarantine, scan them, and use copy package versions to promote only passing versions to the approved repository. Allow developers and normal builds to read only from the approved repository. Option B. Enable Amazon S3 caching in code build. Add a build spec shell script that scans cached NPM packages during every application build. Option C. Provision an Amazon EC2 instance running a third-party private NPM registry. Configure a cron job to mirror npmjs.com and scan packages daily. Option D. Create an AWS code commit repository for each required NPM library. Manually clone public libraries into code commit and reference the Git repositories as application dependencies. The answer here is option A. Create two AWS code artifact repositories in the same domain. A restricted quarantine repository with an external connection to npmjs.com and an approved repository without a public upstream. Use an automated code pipeline/code build ingestion workflow to fetch candidate versions into quarantine, scan them, and use copy package versions to promote only passing versions to the approved repository. Allow developers and normal builds to read only from the approved repository. Let's look at the reasoning. Code Artifact provides managed NPM repositories and can import packages from a public external connection. Separating quarantine from the developer-facing repository prevents normal consumers from accessing a candidate version before scanning. Code Artifact can copy package versions between repositories in the same domain, providing a managed promotion step after the automated check passes. The remaining options can be eliminated because B. Code build caching is not an organization-wide managed package repository and scans dependencies repeatedly during application builds. C. A self-managed registry adds patching, availability, backup, and scaling work. D. Code commit repositories are source repositories, not an NPM package management and public upstream solution, and manual mirroring creates substantial maintenance. If a dependency must be approved before consumption, separate ingestion/quarantine from the developer-facing artifact repository and promote only validated versions. Question number 355. Scenario. A company mandates that AWS WAF must be associated with every application load balancer, ALB, across a production AWS account. ALBs and AWS WAF web ACLs are routinely deployed together using AWS CloudFormation templates. Recently, a developer manually detached AWS WAF from a critical ALB via the AWS Management Console while troubleshooting and forgot to reattach it. The security team requires a mechanism to detect when AWS WAF is removed from any ALB and to automatically reattach it without human intervention. Which implementation provides this capability with the most operational efficiency? Options. Option A. Enable AWS config. Deploy the ALB WAF enabled managed rule. Configure the rule with an automatic remediation action that invokes an AWS Systems Manager automation document designed to attach a web ACL to the non-compliant ALB. Option B. Create an Amazon Event Bridge rule that triggers on AWS CloudTrail modify load balancer attributes events. Route the event to an AWS Lambda function that evaluates the CloudFormation stack drift status and calls the update stack API if the ALB has drifted. Option C. Deploy an Amazon Macie continuous monitoring job targeting the AWS environment. Configure Macie to detect exposed ALBs and automatically invoke a Lambda function to restore the web ACL attachment. Option D. Enable AWS config. Deploy the ALB WAF enabled managed rule. Create an event bridge rule listening for AWS config compliance change events, triggering an Amazon simple notification service, Amazon SNS. Topic to alert the developer to manually revert the change. Go with option A. Enable AWS config. Deploy the ALB WAF enabled managed rule. Configure the rule with an automatic remediation action that invokes an AWS Systems Manager automation document designed to attach a web ACL to the non-compliant ALB. This is the best choice because AWS config continuously monitors resource configurations. The ALB WAF enabled managed rule automatically flags any application load balancer that does not have an AWS WAF web ACL associated with it. By attaching an automatic remediation action to this rule via AWS Systems Manager automation, AWS config will natively invoke the automation document the moment the ALB is detected as non-compliant, reattaching the WAF automatically with zero custom scripting. Let's quickly check the incorrect choices. B. Using EventBridge and Lambda to detect CloudFormation drift and execute update stack is extremely complex and brittle. It requires the Lambda function to have elevated privileges to run stack updates, and stack updates can affect other resources unintentionally. C. Amazon Macie is a data protection service used to discover sensitive data in Amazon S3. It does not monitor the configuration of application load balancers or AWS WAF. D. Triggering an SNS topic alerts a human to manually fix the issue. The scenario explicitly mandates that the mechanism must automatically reattach the WAF without human intervention. Keep this point in mind for the exam. To automatically detect and revert unwanted configuration changes to AWS resources, leverage AWS config managed rules combined with Systems Manager automation automatic remediation. You have completed set 19 of the DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Kaushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.